Video course on statistics. From basics to advanced subjects. Dr. Yahya El-Maghazi, Professor Emeritus at Auburn University, Alabama, USA. Former Dean of Science, Technology, Math, Engineering at Ocean County College, New Jersey. A visiting professor at a number of universities including Rowan University, Keene University, and Montclair University, New Jersey, USA.
Session 2. Numerical Descriptive Statistics.
Part 1. Introduction.
In this session, we will discuss descriptive statistics. And descriptive statistics as a subject is the subject of how to describe data. And as we defined and discussed in the first session, data are numbers that are defined and identified. Describing data is really converting data into statistics, as we mentioned in the introduction.
Perhaps the best way to illustrate the meaning of descriptive statistics is by looking at what I call the info to info cycle, or the information to information cycle, where the first term of information implies the raw information, the unprocessed information, the subjective information, and the second part, which is the other information, is what I describe as the processed or meaningful information. Moving from raw information to processed or meaningful information requires two basic steps. The first step is to take the raw information, which may be subjective statements or some numbers that have no meaning, and convert that into data. And as I mentioned in the previous session, data means factual information. It has to be expressed in well-defined format. If we begin with numbers as the raw information, then the data has to be processed numbers. These are numbers that are associated with definitions as well as units. And I explained that in the first session. I also mentioned in the first session that data can be huge, can be large, and data can exhibit some odd values or outliers. Then to complete the info to info cycle, we have to convert data into statistics. And as I mentioned in the first session, statistics means reducing the massive amount of data that we may have down to few statistics or few measures or few parameters that can describe the entire population. This happens via statistical analysis. And if the analysis are done properly, then the interpretation of the outcomes of this analysis will definitely reveal processed or meaningful information. So that is what I mean by the info to info cycle, starting with raw information or numbers, rumors. People are saying things that perhaps are not totally educated. They are guessing things. Then we have to study the claim or the raw information to verify it by converting it into data, which involves perhaps sampling, perhaps collecting data from some external sources, perhaps relying on the government data, but we have to take the cycle to a real data, factual information. Then we take this data, analyze it, and convert it into statistics, and via the few parameters or the few measures of statistics that we will produce, which describe the whole population, we can reveal processed and meaningful information. The info to info cycle. Let's take an example. Poverty in the USA. People debate a great deal about the status of poverty in the USA. Some people who are living well in the USA do not even realize that the USA suffers poverty or having poor people. Is there a poverty in the USA? In order to convert the general information about poverty in this country into processed and meaningful information, we have to take the subjective meaning of poverty into data, which is the second part of the cycle. We can have the data from the Census Bureau. We can make our own study surveying people poverty or living status. There are many ways to collect data, and there are many ways to sample people for the purpose of the study. And then we can analyze the data, and there are many ways to analyze the data, which is the statistical aspect of the info to info cycle. There are thresholds of poverty in every country. Indeed, somebody living at the poverty level or under the poverty level in the USA may be indeed a rich guy in another country. Now, worldwide, if you are making less than $2 a day, then you are definitely living under the universal poverty. But of course, that doesn't apply to the USA. And as you can see, the thresholds decided by the Census Bureau, we can see that a single person making $12,000 is actually at the line of poverty. If we have two people, it may be 15,000, 16,000. If we have three people, it may be 18 or 19,000. And of course, the number of children added to the family can alter the threshold of the poverty level. Now, we can handle the data, which is typically provided by the Census Bureau of the USA, in many different ways. We can look at poverty by race. And population-wise, as most of us know, there is about 68% of the people living in the USA that belong to the white race. There is about 12% that belongs to the black race, and the Hispanic race is 15%, and then the Asian race, which is increasing in this country, is about 5%. Now, I want to emphasize an important point here, which is the use of a pie chart, because this is a graphical display that we often use in statistics. The key criteria of using a pie chart is when you have variable values that will collectively add up to 100%. So we are talking about a whole population consisting of white, black, Hispanic, Asian. If you collectively add up these you will end up with 100%. That is when the pie chart makes a great deal of sense. On the other hand, if we are looking at the poverty level in each one of these groups, then we will see that we are using a different graphical display, which is the bar chart. And you can see the bar chart here is a two-dimensional graph. The horizontal axis represents the variables or the category. Here is white, black, Asian, Hispanic. And the vertical axis represents the percentage of poverty in each category, as represented by a bar. So you can see how different graphical displays means different things. Here we see that in the black community we have 26.2% people living at the poverty or lower than the poverty level. Now remember, this community represented 12% of the entire US population. The Hispanic community had 24% people living at the poverty or lower than the poverty level, and as you recall, the Hispanic community represented about 15% of the US population. Now, the white community, which as we showed a minute ago, represents 68% of the entire US population, only had about 12.7% of people living under poverty. So we have a problem here. Now, our interpretation to this problem is what's going to lead us to the meaningful or processed information. And different people may have different interpretations of this outcome. If we divide the US population by gender, we have about 51% female and 49% male. And as you can see, we are representing that by a pie chart, which is the most suitable or appropriate graphical display for this type of data. On the other hand, if we're looking at the poverty level at each gender, we're using the bar chart. We have at the female level or the female gender, we have 16.1%, and the male is 13.4%. Personally, I see it as we have a problem. It may look like a 3% or 2.5% only, but we have a problem that female in the USA exhibit more poverty condition than the male. Now we may be able to divide the population by age. And as we can see here using the pie chart, the appropriate display for this case, we have 62% of the US population at the age from 18 to 64. We have 24% of the population at the age of under 18, and we have 14% of the population at 65 and older. Now, if we look at these three categories using a bar chart, we can see that the under 18 has 21.1% poverty level. The 18 to 64 has 13.5%, and the 65 and older has 10%. So what we're doing here is we are really trying to form the complete info to info cycle. So starting with some general information, converting that into data, in this case by race, by gender, by age, analyzing the data using statistical analysis. In this case, we used simple analysis such as determining the percent of people living under poverty in each category. Using simple graphs such as pie charts and bar charts, we were able to reveal some important information, what we call it processed or meaningful information. For example, Black and Hispanic groups have the highest poverty level, 25 to 26%. Female suffers more poverty than male by about 2 to 3%. Under 18 years of age have the highest poverty level, more than 20%, and so on. And we will learn later on how to collect more useful data and how to perform more detailed statistical analysis to reveal much more information than that. But the idea now is we have to understand the concept of info to info cycle. From raw data, raw information, all the way to meaningful information, going through meaningful data, statistical analysis, statistics, and then interpretation of the results of the statistical outcomes. Here is another example, the traffic in the USA. Traffic is getting worse. Once again, to deal with this issue, we have to collect the data. And the data can come from external sources. It can come from highway departments everywhere in the different states. It can come from the Department of Transportation, the Federal Department of Transportation. Or we can do our own study to collect data on traffic issues. Perhaps we can look at the percent of delay, the number of people that get stuck in traffic inside towns and on the highways in different regions, in different cities, in crowded cities, in small cities, and so on. It can be a detailed set of data. And then we do the statistics. We perform simple descriptive statistics, as we will show you later on. We can calculate percent of delay time in different regions, and so on, so we can actually get meaningful information. This meaningful information may include what's been reported in recent years, such as Americans get delayed annually 4.7 billion hours in traffic, serious problem of high magnitude, may require building of more highways and more infrastructure, and it is worth it considering the huge loss of time and the money associated with the traffic issue. Another example, is woman today thriving or struggling or suffering? The only way to answer this question or this raw information is by surveying women. And some studies have surveyed women from all over the world. So we need data. And the data in this case is a survey of hundreds, maybe thousands, maybe millions of women around the world. And the statistics here is also important because this data need to be analyzed so that we can determine the percent of females that are thriving, the percent that are struggling, and the percent that are suffering. And we can see a simple pie chart that can reveal all the meaningful information that we are seeking. And as we can see in this example, worldwide we have 63% of women saying that they are struggling, and only 24% are thriving, and 13% are really suffering. Well, this is worldwide. What if we do this study on a country like the USA or in some of the rich countries in Europe? Would we get the same results? What if we do this study on younger age? That's female under 24 years of age. Obviously, you will get different results. Every time I do that in my class with young women in my class, I find that the majority of them are thriving. They have hopes for the future. So once again, the type of data, the nature of data, and the type of analysis that we perform can affect the outcome, can affect our processed information, can make or break the meaning of the information we produce. Another example, marriage life is simply great. That's a claim. You can hear a lot of people saying that. Is it really great? Maybe you want to verify that. So that is the raw information. We take that into data. And data may be looking at the different social sources about the percent of separation, the number of years that marriage lasts for different age groups, for different races, for different regions in the country, for different countries, and so on. And the data can be analyzed to reveal the percent of separation by age, the percent of separation by religion, the percent of separation by regions. That is how we close the cycle. Going into our interpretation, some people are saying that 57% of couples married today are likely to separate next year. Some data and statistics are showing that marriage after the age of 26, 81% were still married 20 years later. While marriage before age of 26, only 65% were still married 20 years later. These are meaningful information, and they are related to many social issues. That is what I meant by the info to info cycle. How to describe data? Well, this is a long subject, and perhaps the best start is to take a simple example and try to work it out. And one thing good about taking a simple example is that things really do not get much more complicated when we have to deal with a large amount of data. The reason for that is when data becomes large, we rely on the technology. The principles are the same, the concepts are the same. It's just the size of data that requires some technology work to be able to handle large amount of data. And to give you an example that most students relate to, here we have a small sample of students, 18 students, and these are their grades. So this is a data set of 18 students' grades, and we want to describe it. Now, the basic way to describe a data set like this would be to look at the grades number by number or grade by grade and see what we can get out of that. Obviously, this may be possible with the small set of data we have, but things will get complicated when we have a huge amount of data, even if we have double this number or 3 times or 4 times this number of students. So we need to be able to describe a data set regardless the size of the data. Now, there are two types of descriptive statistics as we will cover in the next session. The first type is numerical statistics, and the other type is graphical descriptive statistics. So we can describe the data either numerically or graphically. Well, the fact of life is you really have to describe data using both methods, numerically and graphically. As we will find out, this will be the only way to reveal all the information about the data set. Now, numerical description of data, most of us, even without learning statistics, know how to calculate the average of a data set. In fact, what you see here in the slide is like a scale, starting with the lowest values, going up to the right to the higher values. And the average of this data set somehow describes the center of the data, as we will find out later on in more detail. So this data set has an average of 80. What does that tell us? It tells us that the average grade of this class of those 18 students is 80%. The class, however, has a minimum grade of 60 and a maximum grade of 100. And if we subtract these two values, then we will find that we have a range of 40. So the difference between the lowest grade in this class and the highest grade in this class is 40% or 40 points. And this is a lot. That's a huge range of students' performance. So you see, as I'm reading the data, I'm trying to reveal more meaningful and more processed information. Going back to the info to info cycle, let's not forget that. We can also describe this data set graphically. How? We will learn a lot about how we describe data graphically in more details in the next session. But let us take a simple approach. Suppose we are sorting this data set of grades from the lowest on the top here all the way to the highest in the bottom. We can do that, and once we do that, we can also count the number of students having the same grades. So we can see here that students that obtain 60% are 2 students, students that obtain 70% are 4, students that obtain 80% are 6. We have 4 students who were able to obtain 90, and we have 2 excellent students that were able to obtain the perfect grade of 100. And that's typically what we see in most courses and most grade distributions. Few at the lower grades, few at the higher grade or the highest grades, and the majority or the bulk of the students will be in the middle. Now we can graphically display that very simply using a 2-dimensional graph such as the one that you see here, where the horizontal axis represent the grades and the vertical axis represent the frequency. And what's the frequency? The frequency is the number of students exhibiting different grades. So now if you can put 60 and 70 and 80 and 90 and 100 in the horizontal axis, we can easily find the frequency by counting the number of students exhibiting each grade. As we can see here, here is a frequency diagram or a frequency plot where we have the different grades 60, 70, 80, 90, 100 at the horizontal axis. Corresponding to that is the number of observations or the number of students who earned each grade. So at 60 we have 2 students. At 70 you can see a bar of a height of 4, that means 4 students earned 70%. At 80, we have a higher bar of 6, that means 6 students earned 80%. At 90, we have a bar of a height of 4, meaning 4 students earned 90%, and at 100, we have smaller bar of a height of 2, meaning 2 students earned 100%. This very simple concept is what will form the concept of histogram later on. Obviously, we cannot follow this procedure if we have 100 students or 2,000 students, or if we have numbers such as 60.5 and the 81.2 and 90.3 and so on. So we have to figure out an easier way to handle a large amount of data, and that is the subject of histogram or frequency distribution that we will discuss in the next session. But the concept is the same. You can look at this plot, the simple frequency plot, and you can easily see that at the extreme values of 60 and 100, we have lower bars or lower heights of bars. And as we go toward the center of the graph, the bars keep increasing in height. Later on, we're going to call this the normal data set. This is the normal data set because this type of distribution is what represents most of the phenomena that we study in life. To illustrate this point further, again at this simple level of descriptive statistics, let us take an example of 4 different exams, 4 different quizzes, as you can see here. We have quiz 1, quiz 2, quiz 3, and quiz 4. And each one of these quizzes, we only have 10 grades or 10 students' grades. And let us look at each quiz and try to describe it. Now, this is a simple data set, so any one of us, even without any knowledge of statistics, can describe the data set. Let us look at the first quiz. The first quiz is characterized by values that are all 90%. So what we have here is 10 students took the test and each obtained exactly the same grade. To me, that's an unrealistic data set. To give a test to a number of students and all students obtain the same grade is something very suspicious. But we're going to leave the interpretation to someone else. This is what the data said. Don't ever step over what the data says unless you are the expert now. If I'm a teacher looking at those grades, I'm going to say there is no way that I can give 10 students a test and they all obtain the same grade. Perhaps if you are a student and looking at the grade being that high, you say, why not? We're all equally good. And that will be your interpretation. Let us now look at the second quiz. What we see in the second quiz are more or less values that we expect from a test. After all, different students obtain different grades. But if we look closer, and now that we only have 10 observations in this small data set, if we look closely at this data set, we're going to find something a little bit strange. We're going to find one student who made way below all the students, that's 30, and another student who made way above all the students, that's 99. That normally gets the attention of anybody who's looking at a data set like this one. The rest of the students are exhibiting or having homogeneous grades, 77, 78, 81, 82, 88, 86, but all of a sudden, and without any continuity, we have a student who obtained 30, almost 30 points lower than the next lowest grade, and another student who obtained 99, almost 20 points or 15 points higher than the highest grade. We call these odd values. Later on we can call them outliers. They are likely to happen. They may be 100% true, but they simply do not belong to the rest of the family of the data. These are two odd students. One is extremely poor and the other one is extremely well or good. Let us look at quiz 3 now. Once again, we have likely grades: 66, 68, 70, 92, 90, 94. So what's wrong with these grades? Is there anything that you can observe in quiz 3 grades that get your attention? If we look closely at this data set of quiz 3, for a first sight, you may not be able to see much that is strange or abnormal in quiz 3. But if you sort the data, or if you look closely at this data set, what you will find is something very interesting. You're going to see some grades that are around the 60s. You can see here 66, 68. There are 3 values of 68 and 1 value at 70. And that is one group, while you have another group that are around the 90s. And there is nothing in between. So here we have a data that's split into 2 groups. Groups around the 68 and another group around the 90s. It's almost like mixing 2 different groups of students at 2 different levels. Now between the 70 and the 90 there is 20 points. So where are the students that made 75 and 80 and 85 in this group? We didn't see any. So that's an observation that's worth making when you look at a data set like that. And once again, we only have 10 observations. We only have 10 grades, so we can see all of that by looking at the different grades. If this data set is 50 or 40 or 100 students, we may not be able to detect that very easily. Finally, let us look at quiz 4. And in quiz 4, if you look closely, you will find values that starting at 75, that's a good class, and moving up to 80, then 85, then 90, then 95. You can see a continuity in the data set. You can also see few students making lower grades and a few making higher grades, and the majority are in the bulk or the middle. That is the normal set that I mentioned earlier. The point here is you can, if you have the ability to look at the different values in a data set, you should be able to reveal a lot of information by reading the data and observing the data closely. The challenge is when this data is large. When the data set has 50 observations or 100 observations, or what we see today of flood of information or flood of data coming at us every day. How could we be able to detect these strange patterns in the different data sets? Well, here's the good news. If we can graphically represent these data, we can easily detect all these patterns that I just described. Here is the first quiz. All grades are 90s. Well, if I have a frequency diagram like the one I discussed earlier, where we have a horizontal axis of the grades, vertical axis of the number of students, if all grades are the same, you will have one bar. One bar at the 90%. What does that mean? It means regardless the amount of data. If those 10 students were 100, if they were 1,000 students, but all exhibiting the same grade, you're going to have a picture of a frequency diagram that looks exactly like this one. A frequency diagram with one bar. Let's look at quiz 2. Recall that quiz 2 had two odd values, the 30s and the 99. And once again, you can see when you plot the frequency diagram that the close values are those black bars, but you will see bars at extremes and at a distance from the family of the bars. You can see where is the 30, the red bar, and you can see where is the 99 or the 100, which is far from the rest of the data. For quiz 3, and as we mentioned before, it exhibits a split data or two data sets in one. You can see here in this frequency diagram that there are some bars around the 68 and then another set of bars around the 92, and there is a clear distance between the two sets. Here we know that we have mixed data. We have two components or two groups of components. One group with higher values and the other group with lower values. And by the way, this is a common practical situation. If you mix components that are not homogeneous or are different, that is the kind of frequency diagram you're going to get. If you try to measure human weights and you have adult and you have children, you're going to have two sets of weights that reveal a frequency diagram that look exactly like this one. Finally, the normal data set. You can see here in the diagram smooth continuity from 75 to 95. You have few at the lower grades, you have few at the highest grades, and the majority of grades are in the middle from 80 to 90. That is the normal data set. And speaking of the normal data set, I cannot think of a better introduction to the next session than the normal data set. When we collect data and when we analyze data, we normally assume that this data will be normal. And what we mean by normal is exactly like this frequency diagram that you see. And when you have a normal data set like this one, you can actually draw a smooth curve surrounding these bars, and what you're going to get is what we're going to call later on the normal curve. And from the normal distribution, you can see that there is a need to measure the center of the distribution as well as the spread of the distribution. In the next session, we will be talking about these two types of measures. The measures of data center or the measure of central tendency, the mean, the mode, the median, and others, as well as the measures of variability or the spread of the distribution, such as the range, standard deviation, and variance, and the other measures.
As a result, we're going to use a normal data set as our basic assumption in most of the statistical analysis. And then we will look into deviations from normality later on.